Hey, here's number 8. I'm not really going to do number 8 for you, except to kind of say that it was a giveaway. Why was it a giveaway? Well, let's see. One of the things was it told you the wavelength and the frequency. They didn't have to do that. They could have had you get it, right? I mean, how would you get the frequency from the wavelength? Well, you just divided v over lambda to get the frequency, v being the speed of light. They just did it for you. Also, in case you forgot that the stopping potential in volts was the maximum kinetic energy in electron volts, they just tell you that. Isn't that nice? Yes, it's really nice. Okay, which is the ammeter, which is a voltmeter? We talked about this. M1's got to be a voltmeter. M2's got to be an ammeter, right? M2's got to be in series. M1's got to be in parallel. We plot the graph. I'm not going to plot a frickin' graph for you. I mean, gosh, it's just putting points. But what's important to say is just like it did in lab, it's going to make a line. Now, remember, it means something. It makes a line. It makes a line because if we remember, the energy in equals the energy out, K max plus phi, right? The energy that the light gives it is equal to the energy to free the electron plus the energy to move, which means K max equals HF minus phi. That is in the form of a line. If you think about y equals mx plus b, what do I need to plot to get a line? Well, I got to plot y, which is Kmax, as a function of x, which is just frequency, right? There's no weird frequency squared, anything to linearize. You just plot it. And when I take the slope of that line, I'm going to find h. Ooh. And when I find the y-intercept, I'm going to find phi. Right? And that's what it asks you to do in part C, and you get an experimental value. Notice that that experimental value is going to be in electron volt seconds, not joule seconds, because we had kinetic energy in electron volts. And if the student used a different metal with a larger work function, how would the graph be different? Would the slope, what can be different about a line? Well, there are two things, a slope and a y-intercept. That's all that a line can be, make a line different from another line. The slope can't be different because it's the same Planck's constant. The only thing that's going to be different is the y-intercept, which is the work function. So if the work function were larger, how would the graph look different? Well, remember, the work function is the negative of the y-intercept. So if the work function were larger, it would be a lower graph. So let's say this was the graph originally. Maybe the graph before would be this, right? The graph with a larger work function would be more negative, okay? And that's how that's going to look. But they better be frickin' parallel. Okay. Just for absolute fun, I wanted to do 3 now. I might not be able to finish it, but let's see. Let's start it. We have a free electron with negligible kinetic energy. Okay, that means K equals 0, right? Duh, K equals 0. Which means that energetically, it's like over here. It's got no energy at all. Captured by a stationary proton to form an excited state of a hydrogen atom, right? That means it's going to be somewhere over the ground state. During the process, a photon of energy, EA, is emitted. So it goes down somewhere, followed by another photon of energy, 10.2 electron volts. No further photons are emitted. The ionization of energy of hydrogen is 13.6 electron volts. Okay, we got that? Whew. Determine the wavelength of the 10.2 electron volt photon. Hopefully, that's easy. Remember, E equals hc over lambda. I know the energy. I will solve for lambda. And I get 122 nanometers. You might say, wow, isn't that kind of like a problem we just did? Yes, it is. Remember, the 121 nanometer light at that point, we calculated it was a 10.2 electron volt light. That's amazing. Okay, determine the following for the first photon emitted. The energy of the photon. Well, let's think about this. So we have a photon that drops from here to some excited state, right? Emitting an energy EA. And then it drops again, emitting another photon. So it emits twice. So it drops and then drops again. But it tells us that the second photon emits is 10.2 electron volts. And then it tells us that nothing else is emitted after that. Okay? So that means if nothing else is emitted, that means we must have gotten to the ground state over here. But it dropped 10.2 electron volts. Well, then it must have been 10.2 electron volts above, which means it was over here at 3.4 electron volts. Which means that the first drop must have been over here. What was the energy? 3.4 EVs. See you in a little bit.